In this example, I want to go over how we evaluate a geometric series when all we're given is a bunch of numbers, like this plus this plus this plus this plus this, right? So in previous examples, we were given just A1, R, and told to plug them into a formula. That was easy. Or we were given a summation sign, and we had to figure out what A1 and R were from the summation symbol. In this one, it doesn't say anything about R. You have to know how to find R. I think it's pretty clear what A1 is, right? We should all know that by now. A1 is just the first term. But R is how much you have to multiply by to get the next term in the sequence. So I always just say R equals A2 over A1. And as a little exercise, if you're not sure where that came from, pause the video, go get your explicit formula, and plug in n equals 2, and you can see how I got this. Now, let's go about doing this. Let's say R equals A2 divided by A1. Well, A2 is 36 over 35, and A1 is a negative number, negative 4 over 5. And remember how to divide fractions? I hope. We multiply by the we multiply by the reciprocal. So now we can cross out some terms here, and let's see, 36 and 4 cross out, that leaves a 9 on top. 35 and 5 cross out, that leaves a 7 on bottom. There's still that negative sign. So R equals negative 9 over 7, okay? That's very important. That tells us whether it's converging or diverging. Remember what the requirement is for converging. The absolute value of R has to be less than 1. And if it's diverging, the absolute value of R is greater than 1. So if you look at this over here, you can see that this is diverging because the absolute value of R is greater than 1. That means we're not going to be able to calculate the sum of this series, right? It's going to be a big old DNE because it's infinite. See that right there? That's an infinite series. And when you have an infinite series with R greater than 1, you don't even bother. It's actually a nice problem because it's over very quickly. Let's pretend for a moment. Let's pretend that this were converging. Okay. Okay. So now I'm kind of stepping aside from that initial problem. Let's say R equals negative 7 over 9. We'll just flip it around a little bit. So if you had worked out the numbers this way and you wanted to figure out the sum, let's say it's still an infinite sum. You take the formula, A1, 1 minus R, and remember we have n up here. Well, n is equal to infinity in this case. And when R is less than 1 and you raise it to an infinite power, I think it's easier to think about it in terms of like 1/2. 1/2 times 1/2 is a quarter, right? Times another 1/2 is an eighth. Times another 1/2 is a 16th. These numbers keep getting less and less and less and less. So this turns into A1 times 1 minus 0 over 1 minus R, which this should be familiar to, is the formula for an infinite converging geometric series. Okay, so we're just going to plug in the terms we know. What's A1? Negative 4/5. Great. So we've got negative 4/5 divided by 1 minus R, and R is negative 7/9. So what you have to do in a problem like this, you may be a little rusty in your fractions. Time to dust those off. We have negative 4/5 divided by something. Okay, negative 4/5 divided by this thing. Well, what is that thing? It's 1 minus negative 7/9. That's 1 plus 7/9. Okay, which is negative 4/5 divided by, 9 over 9 plus 7 over 9. Okay, so that's 16 over 9. And not so bad anymore, because now it's just multiplying by the reciprocal. So 9 over 16. 4 crosses out with the 16, leaves a 4 on the bottom. This becomes negative 9 over 20. Okay, and that's how you would calculate the sum of a converging sequence. See, that's actually more difficult than the sum of a diverging series. Diverging is quite nice. You just write down does not exist. But when it's converging, you have to go through the whole song and dance thing with fractions here. And I think actually the hardest case is when it's not infinity, but you have some n right here that you have to consider. You can't just say equals 0. You have to do something else. And I think we've done examples of that before too.